Hopefully by that time, we'll have, we'll have lots of Bruce Willises to go out and save us. A little more seriously, this is it's a big threat, but if you know it's coming, it's actually not that hard to deal with it. Even with modern technology today, that we have today, don't need science fiction stuff. If we could identify an object and have with high confidence, knew with high confidence it was coming towards Earth long enough in advance, it doesn't take that much of a kick, an explosion to change the trajectory of a 10 or a 5 to 10 kilometer or 20 kilometer object, and so that it would miss us. Right? So even though it's a real danger, and you definitely want to have a handle on it, certainly on the time scale of 100 million years, hopefully if we're still around, we will evolve to a level of technological proficiency where this is, really evolved in the solar system and we can take care of it. So I don't see that my worrying about it as long as we keep track of it. Sure. So what's something that's a little bit harder to avoid than in an end of the world scenario? So this is one you probably haven't heard of. But it's quite real and plausible. And it comes back to the sun again. And we're not going to worry about the sun exploding now. That's not the end of energy of the sun. So there's something much more predictable and well-known physics about the sun. So the sun, you see in the sky, you think that it's a constant thing. But the sun's brightness actually changes as it ages. The sun 4.5 billion years ago was about 30% less bright than it is today. And as it ages, it gets brighter and brighter and brighter. And this is well understood from the nuclear physics of how stars work. So the sun is always changing in brightness, and this poses a problem. Poses a problem first when you think about the history of the Earth, current age history. If the sun was much dimmer in the past, then what was the climate like on Earth? And if the sun were dimmer and all else was kept equal, then the Earth's surface would have been, for most of its history, a frozen ice ball. Right? There would have been no oceans. There would have been no rain. There would have been no hydrologic cycle. The Earth would have been a very different planet. It would be an ice ball. But we know from there's abundant geological evidence that the Earth has, maybe with a couple of exceptions, has never been frozen over. There may have been a couple of narrow periods of time where it was frozen over. They're called snowball episodes. So they're episodes. It was never the continual state of the Earth. So how is it the sun was much dimmer? We're very confident the sun used to be much dimmer. How is it the Earth wasn't frozen over? And the answer to that leads us to a chain of logic that leads us to a serious future distant, though, don't worry, again, don't play stop, distant end of the world scenario. So how is this problem solved? Why wasn't the Earth a frozen ice ball when the sun was dimmer? Any guesses? What's that? Earth was hot from the interior. It was warm from the interior, but that's not enough heat to make a difference. So orbit was a little different, but as far as we know, not enough to make a difference.
How about radiation of the Earth?
Radiation from inside or something like that was higher. That's actually why it was hotter, but not enough to change the surface conditions. Atmosphere. What about the atmosphere?
Carbon dioxide.
More carbon dioxide, right. So the best theory we've got, so carbon dioxide, everyone today knows the greenhouse gas that warms the atmosphere of the planet, right? And normally you think this is a bad thing, right? I kind of think about it now. But like so many things, CO2, if it's too much at the wrong time, is a bad thing, but too little is also a bad thing, because it turns out we need CO2 in the atmosphere. Even today, the Earth would be like this actually today if it weren't for the 350 or so parts per million CO2 that are in the atmosphere. Today it's 380 something. You need to have somewhere between 200 and 400 parts per million in the atmosphere today to keep this from happening. In the past, you would have had to have had more. And so the best theory we have is that the atmosphere used to have much more CO2. I'm going to show you one figure. I'm going to waste a few minutes. So here's time. Here's the present. Here's 4.5 billion years ago. So going back in time as we go this way. Here we plot on this axis the brightness of the sun. The jargon is solar luminosity. So here, 4.5 billion years ago, it was dimmer than today, and it's been going up, 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 up. And our best understanding our best guess at what was going on with CO2, so here we're showing the partial pressure of carbon dioxide, how much CO2 there is. So here's today, and if we go back in time, there was a lot more. Okay? Now the evidence for this is actually sketchy. It's really hard to figure out how much CO2 was in the atmosphere 4 billion years ago, but it's the best idea we've got. Okay? And what evidence we do have does fit with it. It's a challenge, but it seems to work. So it seems that as the sun's gotten brighter, CO2 has gone down, and we actually even have a pretty good theory of why that happens. What's mad? Why should CO2 go down when the sun gets brighter? So on geologic time scales, On geologic timescales, this actually works pretty reasonably, because what happens is CO2 is pulled out of the atmosphere by reactions with rocks, chemical reactions with rocks. And those reactions are sensitive to temperature. So the sun gets brighter, the earth gets a little warmer, those reactions speed up, and that sucks CO2 to the atmosphere, pulling CO2 down. And over time scales of hundreds of millions of years, this actually, we think, works to keep CO2 at just the right level to give you nice conditions. So now let's project forward a little bit. The sun keeps getting brighter. The problem is that eventually, the CO2 level is going to get to a level where plants can't photosynthesize. The plants need a certain amount of CO2 to photosynthesize. This will happen, almost certainly. When it will happen is not entirely clear. There's a couple of different papers that are cut off here. One in 1982, one in 1992 that dealt with this. One forecast in about 100 million years. The other forecast in about 1 billion years will reach the CO2 threshold, at which point a biosphere, as we know it, cannot exist on the planet. And you can try to imagine technological fixes for this, but it's pretty hard. You know, it's not as easy as sending Bruce Willis with a bomb. So, 2012, no. 2012 will be fine. Well, I don't know, maybe you have jobs, but you're not dead. So if you want to be more realistic, really, it's like 1 billion in 2012. That might have been a better title, but that's a little tougher movie to make. And you know,